Now, after we opened the hole in the wall, we proceeded to attach the elbow duct. And this elbow duct is what we attached it by, it was pretty tough. It's heavy, I think it's like 500 pounds. So we had like 4 guys holding it up. And we used a jack bolt underneath there to support the weight. And we bolted it in towards the top. And towards the end, to ultimately seal it off, we had the special order flex duct connector. You'll see it right here. That's the flex connector. It allows you to take your original size and expand it to your original size of whatever dimension this is, to expand it to the dimension of that. It also allows you for positioning tolerance. Basically, you can shift it around and have a little jiggle room to work with. Now, the intake straight section. We built the intake straight section by wall on wooden frames. And the wooden frames you'll see right here, we created an extension from the tunnel to the HVAC unit. So we made these walls or these little assemblies, and we have 4 of these. So we put one here, one here, one here, one here. We'll bolt it up, seal it up with silicone, and once we have that done, that straight section done, we're able to attach this flex connector. Now the intake diverging section. Earlier I just said I was talking about the intake straight section. This is the diverging section that comes right after the straight section. The diverging section is right after the straight section. The straight section is right inside this wall. Now the diverging section basically diverges the airflow this way. And it's a little tricky because the walls they're not perfect squares, and we have to cut little triangles that are matched to the right degree of the right angle. And this allowed us to be able to extend from a cross-section of 1 square meter, which was the opening inside here, to an 8x8 opening. I know it's a different change of units, but that's just the way it worked with the HVAC unit and also the wood. So we followed and we expanded from a square meter to an 8x8 opening. Now, to turn airflow, I mentioned earlier that we use turning vanes. So whenever the wind tunnel makes a turn, such as at a corner, especially a 90-degree corner, the airflow can get extremely messy and cause a lot of turbulence. That's when the airflow travels along a path, then when it's about to hit a corner, it just bounces off as it tries to turn. That causes a lot of turbulence, and we want to prevent that in order to have smooth flow. And we want to turn the corner smoothly and to keep the flow laminar. By laminar, that's a vocabulary word. It means smooth flow. And to do that, we use turning vanes. These are turning vanes. They're custom made. And these turning vanes have multiple aluminum flaps that gradually, if you see the curve here, it gradually turns the airflow to avoid sharp corners. Now, this turning vane is used in multiple corners of our wind tunnel. And in this case, this is a smaller section of the wind tunnel. We have diverging sections, contracting sections, and so there are certain parts of our tunnels which are smaller in the cross-section and some are larger. Now, on the smaller contraction, on the smaller tunnels, in the corners, we're able to use only one. That's enough to turn the airflow around. Now, in large sections like the 8x8 that I mentioned earlier, we put the turning vanes in a stack of 4. So we have to secure it down with bolts and screws, and that's how we use to bolt it down. Now, one thing about the airflow is that when you're running a test, you want to have clean airflow. And you want it to be clean because you want it to be laminar or smooth. And in order for it to be laminar, you have to minimize your flow turbulence. And you clean this airflow by installing filters that clean the air in each direction in a 3D perspective. By 3D perspective, I mean that if an airflow is coming this way, you might have some turbulence that's just floating around. You want to be able to clean it this way, and this way. So therefore, you use a honeycomb filter or a screen filter or both. A honeycomb filter cleans the air in the z-axis. A screen filter cleans the air in the x and y-axis. Now, clean the airflow. I just mentioned about I was talking about honeycomb just now and streams. So a honeycomb is basically an aluminum sheet that's shaped like a honeycomb. It's about 5-6 inches thick and allows you to put your air through it and clean it in a horizontal way. The screens are also attached to 2 frames that are made together by 2x4 studs, and the honeycomb were also placed on these frames too. And we were able to slide these into our test section to filter the air before it reaches the test section, before the anechoic wind tunnel chamber. Now, cleaning the airflow. When we completed this, the screens and honeycombs can now be easily removed for maintenance. And it's easily done by just sliding them out. It's a little heavy, but all you have to do is just slide it out, change the screens, clean it, whatever you have to do. There's the first screen here, second screen here, and the honeycomb right here. It's a little difficult to see on screen, but it's right there. Now, later on, after we put on siding and other stuff like flashing, we made a custom door that allowed us to cover up this hole with a little door, and that allowed us to waterproof it and protect it from rain and all sorts of weather damages. And by having this door here with handles, we can just remove it for future maintenance. For exhaust section, at the rear end of the wind tunnel, we wanted to design a section of the tunnel that can extend into the fan unit. And earlier I said that this is a fan unit. So basically there's a large fan in here, and there's a metal plate here. And we want to finish extending this inside. So what we ultimately did was we cut it with a abrasive disc and cut a hole in the metal. And I don't have any in-progress pictures. I've got to take some pictures, but it's ultimately it took a few days. And the other side is the opening of this side, this picture here. And once we completed it, we had a door. We also designed a door that we can just latch and open and close. That way we can allow easy access into the fan unit if we want to do maintenance. Now the external finish. By external finish, I mean protecting the outside structure from weather damage, rain, snow, anything. To do that, we use siding to cover it up, and we use metal siding to cover the external walls on the outside of the tunnel. And these external walls are originally they were exposed as wood, and what we did was we put more 2x4 pieces in here, so we can just nail these or screw these metal sidings in. And we use what we call flashing. Flashing is a metal sheet that you can buy in the roll, and we roll it down and bend it over so you can have this nice finish over here to prevent water from seeping under. Now we also did roofing on the tunnel. We wanted to add the roof because you can protect the roof from rainwater and water damages, all sorts of stuff. To do that, what we did was we laid down a layer of tar paper and we nailed it down. And then we added a asphalt sheet, which is what you see here. So the tar paper is right underneath here. And that was also secured by nails. And then on top, it was also either secured by tar on the top here or along the edges. And we did this all around the other sections of the wind tunnel, but for this picture itself, I wanted to show you guys this because this is the converging section, the diverging section that we had earlier. This is where the HVAC unit is and where the elbow goes in. So this is how we covered up the roof on there, and we made these custom rain guards that allows you to channel the water away from the edges. Now for a chamber exhaust. So the anechoic chamber, this building inside, this concrete building, the actual facility is inside, and this is the outside. This is the exiting hole. And in order to channel the airflow through here and around the building towards the other side where you got the exhaust fan, what we did was we constructed a wooden box, and that basically is constructed out of a 2x4 frame and also plywood. And these frames will be placed on here with the wood on there, and then it will basically create a box. And once we installed it, we put the frame in, put the wood in, and secure the bottom with bolts, washers, nuts, and on top we layered it with our roofing. And finally, it's watertight, water sealed. We sealed the side with caulking and silicone, and now it's waterproof. Now, sound reduction. Earlier I was talking about the anechoic chamber and how it can reduce a lot of the noises. Well, the way it works is that it has these wedges, and in our facility we use fiberglass wedges. And they're little wedges that have a sheet of thin fiberglass material that folds over it. So you get 3 wedges per aluminum frame, and each aluminum frame is attached onto the wall on these aluminum tracks. And that's how you secure it and create this room. Now, for further sound reduction, we also installed an acoustic insulation, which is basically sound absorbent material all along the inside of the tunnel. And you can see here from a previous image where you have the turning vanes here, and also the exhaust section where I just showed you. There's an acoustic insulation all over, and that's designed so that it allows it to absorb any sound that might be created by airflow moving through the tunnel. Now, currently we're working on the air collector. We've worked on so many projects over the summer, and we've gotten a lot done. And right now, as of the last week, we've been starting on the air collector, and we're basically creating an air collector, which is a device similar to a funnel. So you have this airflow coming in, and you want to make sure that you're able to extract all the airflow out and eject it from the facility. And you do that with a collector. It acts like a funnel. And at the moment, we have the basic frame done. Next week or so, our next step is to construct the funnel. So you're going to have something that opens up this way, and it'll be sort of like a cup or a collector or a catcher that allows you to suck out the air that are coming in. So this is an image made in SolidWorks by one of our students, and I just want to show you how this all comes together. And overall, I've shown you a lot of pictures of different parts of the tunnel, but here's the overall layout. So this is the building where you saw the HVAC unit before and the elbow, and that's where the air comes in, gets redirected into the diverging section. It passes through the diverging section, turns in the turning vane, goes straight, then turns again, and goes into the converging section where it's going to be channeled into a straight section that we're going to build in the near future. And that's going to channel it to our test section, which will be located right here. The collector, we're going to build it right here. And the air that flows through here is going to be rechanneled through this path. There's a turning vane here, straight path, turning vane, straight path, all the way into our fan exhaust unit. So one question that we might have is, what kind of wind tunnel is it? Well, the way it works is that you have air coming in from the atmosphere, and you have air exhausting into the atmosphere. So this tunnel is actually an open loop tunnel. So our future studies is to finish this air collector. We have to finish designing it and also finish assembling it within the next 2 weeks. And after we finish that, we want to reinstall the fiberglass wedges that we have to remove in order to access the walls of the building. Then once we finish that, we want to build the straight inlet section, which I just mentioned just now, down here. And we want to mount it inside the chamber. And then once we do that, we want to modify the straight inlet section so we can increase the airflow. And the reason is because we ran a simple test and we studied the actual velocity that's coming out of the wind tunnel. We achieved 6.5 meters per second. We needed 5 meters per second, but we're aiming for 10 to 15. So it's a little bit slower than we expected. So in order to increase speed, one alternative we came up with is to modify the inlet straight section so that you can minimize your cross-section and increase your airflow. Now we also want to finish installing the siding on the other external walls, as well as flashing and also the roofing that we might have missed. And then we're going to seal off and finish off the elbow duct area in the HVAC unit. That's where the elbow duct was earlier, and we want to seal off so it looks nice and presentable. I want to thank Dr. Mark Lauser, Gunnar Wang, Jacob Waltad, Chris Walters, Syracuse University, Dr. Stack, and all of our Mission Society staff. Thank you. Questions?